First off, I wanted to thank AWC for allowing me to speak to all of you today, and of course, I want to thank everybody in attendance for joining our webinar session, and hopefully we can get through this and we can all learn something along the way. Force transfer has been a hot topic in the design industry for some time now, so I'm glad to be able to share some of the newest design and testing results that we have for you. So without further ado, let's get moving. Here is our obligatory, statutory, mandatory AIA credit registration statement. Everybody listening in should receive a certificate for the course. So hopefully you guys have read through this. Here is our AIA approved course description. I will not go through all of this for you guys today, as I'm sure you read through it while signing up for the course. To start with our learning objectives, first we'll look at the past and current methods for determining force transfer around openings using wood shear walls. Since force transfer around openings is accepted in code as the only method based on a rational analysis, there's a variety of methodologies available that engineers use regularly. Next, we'll look at the effects of different sizes of openings and full height piers, the different code allowable height to width ratios or aspect ratios, and how that impacts all three currently accepted lateral design methodologies. We'll look a little more in depth into how the aforementioned testing allowed us to analyze the internal forces of the modeled shear walls and how that led to the accuracy comparisons between calculated and tested values for force transfer around opening methods. And lastly, we'll focus more so on the testing results that allowed for the creation of the new design methodologies and how they will allow us to accurately design for multiple openings and asymmetric piers as we move forward. So as Marcy stated, here's our first audience poll, just to get a gauge of who is in the audience.
Okay, so first of all, what is your profession? As always, we kind of go ahead and get started just assessing who we have. And I've got about 70% of you have voted already in the first 10 seconds. So you guys are fast. That's awesome. All right, since we have a lot of information to get through, I'm going to go ahead and close the poll. And I'm going to share. So we have 81% of you are engineers, 12% building officials, 4% other, and 3% architects, no builders. So welcome to all of you. We're so happy that you're here. And then Jared, right back to you.
All right, again, thank you all for joining us. That jumps us right into our next audience poll question. So back to back.
All right, and again, how would you describe your knowledge of force transfer around openings? So are you an expert, intermediate, novice, or what am I doing here? So, and if you're at that point of what am I doing here, you're going to learn a lot today. So. All right. I'm so pleased. All of you are very fast today. 85% have voted in 30 seconds. I'm going to go ahead and close and share again. All right, so we've got 50% feel that you're intermediate, 41% novice, 6% expert, and 4% what am I doing here? So Jared, we're somewhere in that middle range, you know, intermediate to novice. So.
All right, great. Hopefully that 6% can email me some extra information at the end so we can all help each other out. So looking at this, here's our agenda for achieving the aforementioned learning objectives for the seminar. We're going to look at shear wall design challenges. We're going to look at the history of force transfer around openings research. We're going to look into the advancements in the force transfer around openings research, including asymmetric piers or piers of different widths, multiple openings in a wall line, C-shaped panels we will touch on, deflection calculations, and then the conceptual keys that came out of the testing that we did for FTAO. And lastly, some of the benefits that FTAO and continuously sheathed wood structural panels have for your shear wall systems. So as structures are becoming more complex in the growing economy, designers are often searching for better options to accommodate the structural design. One of the most challenging aspects of this design is the lateral resisting system, right? We're consistently seeing larger buildings, larger openings, and which usually translate into reduced locations for lateral resistance, making it harder and harder to stay within the 2-to-1 aspect ratio of our shear walls. What we'll examine here today is how FTAO will allow us to solve these puzzles by utilizing more of the accessible wall framing to aid in the resistance of these lateral loads. So before heading into the laboratory, we began by performing numerous field surveys to see how things were being done. As you see in these photos, buildings and houses have a lot of design interests, creating more and more complex facades. Although architects usually get most of the credit for these, it's our job as the structural engineers or designers to make these complex facades work. In the upper left, we see probably the most common application for FTAO, the multifamily apartment structure here, where you see walls that are in and out of plane, multiple openings within a single wall line, typical application, right? But there are many ways in which force transfer can help us in residential industry as well. Accommodating larger openings is shown in the bottom left, potentially replacing some of the pre-engineered systems by allowing for narrower segments, and allowing for openings that are not stacked floor to floor or that have some restrictions in other applications. So before we focus on force transfer, let's look at our full spectrum of shear wall choices per the seismic design provisions for wind and seismic, or SPIDWIS, which is part of AWC's National Design Standard. In SPIDWIS 4.3.5, it defines the different shear wall options. You can do a segmented approach, a perforated approach, or force transfer around openings. And we'll compare and contrast these to begin, especially for those of you who do not do wood design as regularly. So we'll begin with the segmented shear wall, as shown on the far left. Your aspect ratio in the past was 2-to-1 for a seismic control design without a penalty, up to a 3.5-to-1 ratio with a reduction. Well, the code change for 2015 made it so that you have to apply this aspect ratio to buildings nationwide, regardless if it's high seismic or high wind. So we will go into this in greater detail in our examples a bit later. For the segmented wall, what you notice if you look closely at this picture is underneath these openings, we have open studs, right? So for this design, they most likely used a segmented approach, as they have the stacked wall systems with nothing going on in between the shear wall resisting. In both force transfer round openings and the perforated method, you look at the wall as a whole. The entire wall is utilized as a shear wall with openings provided inside the shear wall. The way you do the design, however, is different in the fact that the perforated approach is an empirically based method. This is based on testing that originated in Japan and was further developed in the US by AWC, Virginia Tech, and the APA. For the perforated method, you look at the percentage of your full height wall sheathing in the wall line and the maximum size openings, and based on those two variables, you'll select a capacity adjustment factor. And we'll look at this a little bit later as well. Basically, this is a reduction or a penalty that you apply to your shear calculation, your hold downs, and your anchorage at the bottom of the full height wall pier segments. So that's your perforated approach. Finally, for force transfer, which is what we're going to focus on today, it was not based on testing historically. Instead, it's based on the rational analysis, and that rational analysis can vary quite a bit from design office to design office, or even engineer to engineer within an office. What you generally will see in the field is that the straps on the exterior of the wall will be generally above and below your opening, and that's going to be transferring the tension forces through the wall. And then there's blocking on the inside of the wall, transferring the compression forces. And the sheathing, which is not just for the full height segments, but also above and below your openings, transfers shear and all of the forces together through the wall to the hold downs at each end of the system. So it's important to note that even though we are focusing on FTAO today, you don't have to pick one type of shear wall for your entire structure. You can mix and match story to story, wall line to wall line, whatever you need to do to get the best fit for your project. So starting out, as I said, we'll do a little review. So as shown before in the comparison, for the segmented approach, you only use the full height segments. So only these full height segments can apply to the effective lateral resistance. The aspect ratios are typically height to width ratios using only these full height segments. Typically with a segmented approach, we also have to place hold downs at each side of every wall pier in order to resist our tension and compression forces. Another item to note here is the fact that the aspect ratio adjustment has changed. The requirement for the adjustment penalty used to only apply to high seismic areas. Now, in the 2015 SPIDWIS, if you exceed a 2-to-1 aspect ratio, an adjustment is going to be applied globally for all shear walls, regardless of seismic or wind. It no longer matters if you're designing in LA or Boise, Idaho. If you're designing for seismic or wind, if you exceed that 2-to-1 aspect ratio, your shear wall has to have an adjustment factor. And then you can go up to a 3.5-to-1 adjustment maximum. The adjustment factor, however, now also has options, which we'll go over a little bit later. So going to the perforated approach, waiting for it to catch up here. We're looking at this as a single shear wall. So you only have 2 hold downs now at the outside of the shear wall. And your Vmax shown here at the bottom of the wall is calculated based on the unit shear, based on the sum of the full height sections. So we're still looking at the full height sections of the wall for our aspect ratios. So again, that's another challenge with the perforated shear wall. It's measured the same as it is for the segmented approach. Your height is based on the total height of the wall. And in this case, only the full height segment widths adjacent to the openings count for your height to width ratios. So this brings us to force transfer around openings. Looking at the basic design here, you'll notice we have a hold down at each end of the wall, and the sheathing is provided above and below the opening, similar to what we saw for the perforated approach. But the sheathing provided the shear resistance attachment at the top of the wall, straps above and below the opening, blocking on the inside, which you can't see, help to resist the tension and compression forces inside the wall. The main advantage to the force transfer around openings is how the height to width ratio is defined. So as we showed on the perforated and method and the segmented method, we use the full height of the wall. For the force transfer around openings method, we're only utilizing the height of the wall adjacent to the openings. So this can help. Our walls are generally 8 to 10 feet in height. So if you want to meet that 2-to-1 aspect ratio to avoid an adjustment, we're looking at a 4-foot or 5-foot minimum segment width. Looking at force transfer around openings for that same 8 to 10 foot wall with a 4-foot tall window, the wall height is not as important as we focus on the 4-foot window height for our wall pier, and you could go down to 2 feet and still meet your aspect ratio of 2-to-1 for that panel width. This is, in my opinion, the largest advantage and one of the driving factors of why structural engineers use force transfer around openings. It's in these situations where the height to width ratio will not work for other applications, so we try to find the alternative method. So this brings us to our next audience poll.
Marcy? I'm so sorry. Thank you very much. All right. So how often do you use force transfer around opening when designing a building utilizing wood shear walls? Is that more than 50% frequently, 0 to 25% at least once per job. 0% you only use segmented or perforated, or you don't design wood buildings. So again, 75% of you have voted in the first 20 seconds. So you all are very fast. All right, I'm going to go ahead and close. And let's see. So 41% do not use force transfer around openings. You only use segmented or perforated. 26% don't design wood buildings. 22% use 0 to 25% or at least once per job, and 11% use it more than 50% or frequently. So, all right, Jared, back to you.
Okay. So here we want to look at the aspect ratio adjustment factor changes that I noted on before, and the deflection requirement changes for the new 2015 SPIDWIZ. As I noted, instead of applying that adjustment factor only for the high seismic structures, now all shear walls that have an aspect ratio greater than 2 to 1 but less than 3.5 to 1 shall apply a reduction factor. The old reduction factor was 2 times the actual width divided by the height. In section 4.3.4, there is a new aspect ratio factor as shown here equal to 1.25 minus 0.125 times the height divided by the width. So for the old factor, where aspect ratio was 3.5, the adjustment factor was 2 divided by 3.5, which equaled about 0.57, versus the new 1.25 minus 0.125 times 3.5 gets us about a 0.81. So we're looking at about half the penalty when you look at the new aspect ratio adjustment. The difference is, with the new aspect ratio adjustment, you also have to make sure that all of the shear walls in that line have the identical deflection. So you may or may not be aware of this in SPIDWIZ section 4.3.3.4.1, which states that individual shear walls in a line shall provide the same calculated deflection. So that's what I was talking about. Each design utilizing the new aspect ratio adjustment factor shown in 4.3.4 must also conform to this provision. This creates an additional step to using the less restrictive adjustment, as we now have to ensure that each wall segment used to resist shear loads in the same wall line has the same calculated deflection. So as a note, you do not have to perform this check if you have shear walls using the historic adjustment factor or shear walls that exceed 2 or that do not exceed that 2 to 1 aspect ratio. So another clarification for the new 2015 SPIDWIZ that's useful to note is with the perforated approach. In the past, the question would come up, if some of my walls meet the 2 to 1 aspect ratio in my perforated shear wall, but not all of them, do I need to apply the adjustment factor to the entire wall, or do I just apply that adjustment factor only to the full height segments? Well, in the 2015 SPIDWIZ, section 4.3.4.3, it has been clarified that you're going to apply the adjustment only to the individual wall segments. So if we look at this diagram here, say L4 and L1 were a 3.5 to 1 aspect ratio, where L2 and L3 are 2 to 1. You would only apply the factor to the length of L1 and L4. Those would be the only ones that need to be adjusted. You would not have to do it to L2 and L3. And it's less of a penalty than in the past, but also you have to make sure, if you use the new aspect ratio adjustment factor, that you're making sure that all 4 of these shear walls have the same deflection across the wall line. So now with that, it brings us to our 4th audience poll.
All right, so here we go. When designing shear walls with the new aspect ratio factor of 1.25 to 0.125 H/BS, the deflection of each shear wall must be A, less than 1 inch, B, equal, C, dependent on the wall material, or D, a parabola? All right. Okay, I'm seeing a definitive answer, so I hope that this was an obvious answer. So, all right, I've got almost 80%, but also 40 seconds, so I'm going to go ahead and close. All right, so 86% said equal, 7% less than 1 inch, 6% dependent on the wall material, and 1% parabola. And the real answer, Jared, is?
The correct answer was B. So when applying that new aspect ratio adjustment factor, you have to make sure that all of the walls inside your individual shear wall are equal to each other. So as noted, we went into the field as well as into the design offices to see what was being used before we began our research study in the laboratory. Based on a field survey in Southern California for 18 plus job sites in multifamily and single family structures, we found out that our multifamily jobs, typically 40 to 90% of all of the shear applications, use some amounts of FTAO. The single family structures, around 80% had at least one application on the front or the back elevation. 70% had multiple applications, front, back, or both, and 25% had a sidewall application in addition to the front or back. So if you think about this, most of the homes that we design, where are the largest openings, or the majority of our openings? They're typically in the front or the back of the house, right? So this makes sense as to why we saw the need for force transfer around openings that was going to be used on narrow segments with taller heights, and also ratios based on the number of openings, which drive us to the requirements for our FTAO. So the joint research project was done with APA as well as the University of British Columbia and the USDA Forest Products Lab. The University of British Columbia provided a finite element analysis component to the projects. They replicated the same testing that we did physically in our laboratory with a computer model to show the same results. The Forest Product Lab provided oversight and a managerial aspect. The goal was to look at the variations in walls with different code allowable height to width ratios, the 2-to-1 versus the 3.5-to-1, different sizes of openings, different levels of detailing, and different wall panel widths. We only sheathed the full height segments to do a segmented approach, or did they sheathe the entire wall and not have the full hardware as a perforated wall versus full force transfer around openings with strapping and blocking above and below? So we wanted to look and compare all of the current design methodologies. So in addition to recognizing what was done in the field, we wanted to compare that to the rational analysis techniques that are typically used by structural engineers to identify the most accurate rational analysis method. What I mean here is that we wanted to see which of the current force transfer around opening techniques would calculate the closest strap forces to those measured in the laboratory testing. Anytime APA does research or tries to bring something into the laboratory, our goal is to make things better for the construction industry. We want to help engineers create accurate designs faster, help contractors to be able to build more efficiently, and potentially make the entire process more efficient for all parties involved. So to start off, we want to look at all the different techniques that are currently available for force transfer around openings. So when we talk to designers and went out into the field, we looked at the top 3 that were the most common force transfer around opening techniques currently being used. So first we start with the drag strut analogy as shown here in this simple diagram. You're dragging the loads above and below the opening and using the geometry of the wall to concentrate those forces. We concentrate those forces into the corners and calculate the corner forces based on that. For the cantilever beam analogy, you take the same wall, but now we're going to break the wall into segments and then sum our moments to solve for the forces of the corners. So thinking about this, if we look at the moment that we are going to be calculating based on the geometry, and we apply this to a typical wall that we see, okay? Where do we tend to have more sheathing, above our opening or below our opening? Typically, we have more sheathing below our opening, right? So when we're calculating our moments and summing for the corner forces, we are going to tend to calculate a greater force above our openings where we have less of a resisting arm. Less sheathing equals less resistance, okay? So using this technique, we will typically end up with a higher strap force above our openings. So we keep that in mind also when comparing the techniques to one another. So I think the most common technique is the Dieckmann technique. Basically, this technique is solving for the internal forces of the wall by way of principles of mechanics. We break down the wall into smaller individual segments, and using simple statics, we solve for the forces in each of the segments. Once resolved, we put all of the pieces back together to calculate the overall forces on the wall system. So some of you may also be familiar with the Thompson or the Seock method, which is similar to this method, but yields slightly different results. So that brings us to our next audience poll question.
Yes, it does. And here we go. All right. In which force transfer around opening method are the forces determined by calculating moment couples? Is that the drag strut analogy, cantilever beam analogy, Dieckmann-Thompson, or the unicorn method? All right. I think the questions are getting a little harder. People are going a little slower. So, or maybe we're getting tired. It's that time of afternoon. All right. So I've got about 35 seconds and 79. There we go, 80%. And so we've got 58% say the cantilever beam analogy, 27% say the Dieckmann-Thompson, and 14% drag strut analogy, and 1% the unicorn method. All right, and Jared, the real answer?
Yes, so the correct answer is B, the cantilever beam analogy method. So this is the one where we talked about resolving the forces by moments and seeing how it would equate into the strap forces above and below the openings. So moving forward, if we apply this to a simple wall example, and this is just for resulting forces and seeing what those would be between the three methods, we'll get into a full example here in a bit. For this wall, we have a 2,000 pound shear force at the top of the wall, a 2'3" width for the first wall pier, or 4-foot opening, and a 4-foot end wall pier. So we have those asymmetric wall piers. 2 feet top and bottom. So this is asymmetric wall piers and unrealistically the same height of sheathing above and below the opening, but just for a quick reference purpose. So overall length of the wall is going to be 10 foot 3 inches, and the wall height is 8 feet. So running the analysis for all three of the FTAO methods on my program TI-89 to evaluate the corner forces at the openings, we find that the drag strut analogy yields forces of 284 to 493 pounds. The cantilever beam analogy resulted in 1,460 pounds per foot, or 2,540 pounds. And the Dieckmann method, 567 to 986 pounds. So looking at the numbers, we see quite a bit of spread between the results, which could also alter the strap selection for the wall. So the questions are they all correct? Are they all incorrect? Which method should we be using? And those are the questions that we set out to answer with our testing. So I know that was quick, and if for more information on any of the methods or the full calculations for that small sample. Feel free to send an email out after this or just leave a comment and we can make sure that we send that out to you. We also have some other resources. Part of what initiated this research was an article written by Zeno Martin, one of the APA's research engineers. This was in wood design focus. So the first two references shown here are that article. Ed Diekman actually wrote back to Zeno Martin via the magazine in a closure response to the original article. And the Diekman technique is also very well described, the Breyer textbook. And I'm guessing many of our offices have that as well. So the last reference that is shown here, I'm guessing some of you may have, but these are the Seoc-Thompson method and what is formerly known as the Seoc seismic design, or there are the Seoc seismic design manuals, and these are available via the ICC website. So to answer the questions of accuracy, we took all this knowledge of FTAO into the laboratory. So as you see this picture, this is a typical setup for our laboratory. You see OSB sheathing used for the wood structural panels above and below the openings and on both sides. We have actual hold down show here replicating the flat strap and many monitors attached to the wall in a variety of places. So you'll notice as we go through our testing and wall configurations that we are constructing our walls with these hold downs on the exterior of the walls. This is coming up in the 2018 code changes. Okay. No, I'm just kidding. Don't take that seriously. We're not crazy. We do anticipate that anybody building FTAO walls, they're going to use flat strappings. We don't expect anybody to use it this way, okay? The flat straps are going to be used in the field, and these hold downs were specifically used for the ease of replication in the testing and monitoring, and it also allowed us to attach more of the monitors to the hold downs than we could with a flat strap. We did additional testing, which I can show you the wall here in a little bit, that has the flat straps to prove that we were going to achieve the same results and that the hold downs did not alter our methods. So I just wanted to point this out to you before getting too far along so that everybody wasn't thinking we were crazy and going for something completely different. But if you decide to use those hold downs in the future, it is tested and completely approved, so that's completely up to you. So all the walls were built 12 feet long, 8 feet tall, and we had 12 different wall configurations that were tested, some with force transfer round openings and some without. The wall nailing was 10D common nails at 2 inches on center for all of the walls, and we used 15-30 seconds performance category structural 1 OSB. You also may be asking yourselves, why did we select these particular materials consistently? And the reason why, if you're familiar with the history of the perforated wall, which is the one that we spoke about earlier that was tested in Japan, you can recall there was a limitation to the maximum shear you used to be able to use in the past. And that was based on the testing that they did for perforated shear walls. They had only tested it to that level of the shear capacity. So we didn't want our research to be limited based on us selecting a lower level of OSB or nailing or whatever component. So we took it to the top of the chart using the structural 1, 15-30 seconds OSB, and the 10D nailing. We also chose OSB versus plywood because there are some people in the industry that believe that plywood is a superior product to OSB. And if we had done all of our testing with plywood, those people may have felt that we couldn't apply this to our structures because it was tested on OSB or on plywood and not OSB. So it's not the same thing. But we wanted to prove that OSB, plywood are identical in capacity and also that it could be used for either of the materials. And the 10-penny nail were the same as the first argument. We wanted to get to the maximum shear capacity. So that's what we used. All of the walls were tested using a cyclical loading pattern and the Curie basic loading. So as I go through our wall configurations, I'd like to highlight just a few of these for us to look at. I'll touch base on all of them, but if you're interested in reviewing any of the configurations in more detail, the full research report is available on our website. So beginning on wall 1, we were looking at the segmented approach. You see we have our 3.5 to 1 aspect ratio for our wall. So we end up with the 2'3" pier lengths on either side. There was no sheathing above or below the openings. Sheathing only for the full height segments with hold downs at either end. Wall 2, we added sheathing above and below the opening and removed the interior hold downs, enacting the perforated method. Wall 3 is the same as wall 2 with the addition of blocking at the interior side. And if we look at wall 4, we're building up to that full force transfer round opening detailing. It's the same geometry as walls 1 through 3, but now in addition to the sheathing above and below the openings, we have the strapping at the exterior of the wall and nailing as appropriate. So now if we move on to walls 5 through 8, wall 5, we've done is taken wall 4 and increased the size of the opening. We'll blow up wall 6. It's also similar to wall 4, but if you look closely, you will notice the C-shaped panel at the left side of this diagram. Typical wood structural panels are usually 4 feet by either 8 feet or 10 feet long on a job site. So for this wall, we had the 2'3" piers at either end. Part of what we saw a lot of in the field study was the fact that these openings were being cut out of the panels in place, creating these sheath-shaped areas of sheathing. Seeing this, we wanted to see how or if this would react during testing. We wanted to find out if having that C-shaped panel contributed to the force transfer around openings and if the panel helped transfer the load. I'm not going to spoil the results now. We'll go over this in a bit. So looking at walls 7 and 8, wall 7 is similar to wall 1, but we are getting our basis for the 2 to 1 aspect ratio in lieu of the 3.5 to 1 aspect ratio. So wall 8 is wall 7 with full force transfer around openings detailing. So looking quickly at walls 9 through 11, wall 9 is basically the same as walls 7 and 8 that I just showed you, but we have enlarged the opening once again to analyze the effects on the strapping. Wall 10, we wanted to analyze a larger door opening using FTAO. Wall 11 is the same as wall 10, but if you notice at the bottom, we've removed the interior hold downs from each pier. So again, we'll blow up wall 12. If we look at wall 12, our last segment configuration, the configuration is what really provided us with some of our greatest information as far as going around multiple openings and asymmetric piers. You'll notice we have different pier lengths for each of the full height segments. We have the full force transfer around openings detailing, one hold down at each end of the shear wall, strapping above and below the opening, and you can't see it, but there's blocking on the reverse side of the strapping at the interior side of the wall. So through all of this, what information was obtained? We monitored the different aspects of the building from the anchor bolt forces, hold down forces, strap forces, and wanted to collect all this information. We evaluated the displacement of the elements versus the load that was applied and provided hysteric plots for all of this information. And we'll see some of this in a bit. We used a reference deformation of 2.4 inches, which allowed a maximum of 4.8 inches on the wall system as a whole. This reference was simply based on some of our historic testing and conclusions that we've drawn from shear wall testing throughout the years. And then our results. What you see here is an example of our charted test results for all 12 wall configurations. This chart shows the predicted strap forces versus the strap forces measured during our testing for the horizontal strapping above and below the openings. For the purposes of this presentation, it's not as important to be able to read what the actual values are, but more so to focus on the color coding that we're showing here in this table. So the strap forces were measured during testing to gain a comparison between the common FTAO techniques that are being used today. And as we discussed earlier, we have the drag strut technique, the cantilever beam technique, Dieckmann technique, and you also see the Seoc-Thompson technique at the end there. So we use the test to compare the measured strap forces versus the forces that were estimated using all these different calculation techniques. What you see is that the yellow cells represent items that were underestimated. If the strap forces were estimated to be less than what was measured, it's identified with yellow blocking. If the strap force values were overestimated by greater than 300%, it has a green color code. So just glancing at this table, we can see quickly that the drag strut technique, although it's relatively easy and many of us have used this method, the results are an unconservative batch, right? We don't want to be unconservative as designers. So on the other hand, looking at the cantilever beam technique, it's primarily green. This shows even more so on the top force, where we were talking about with the cantilever beam technique, resolving those forces at the top of the wall will give us higher strap forces above the opening with less sheathing. So seeing this, we can recognize that we probably don't want to use the method because it's overly conservative. If we are trying to establish a balance between strength and economy, this design is probably the least economical for our clients. So that leaves us with the Dieckmann or the SEOC techniques, which aren't the most straightforward to use in most instances. Many of us have spreadsheets to automate this in our offices, but it's a good takeaway to note that really is the most accurate rational analysis technique to date. So we focus on the Dieckmann technique. Another thing to note is when you look at wall 6, the wall that I showed you before that had the C-shaped panel at the opening. If we look at that wall only for the drag strut method, you can see that it actually came out to be one of the closest, most accurate methods. This is because the panel was actually working to help transfer some of that tension force, which made it match more closely to what was estimated per the drag strut technique. All the other techniques were considered way overestimated on that wall. So the C-shaped panel really does provide us some design assistance and something to consider moving forward if you plan to use the drag strut technique. You can incorporate the C-shaped panel into your detailing to help offset some of the unconservative nature of the design. We currently don't have anything in place to help with that design right now, but using the rational analysis, you can help use that to move forward. And as mentioned before, here's a photo showing the flat strapping that was also done in the lab. You see this is wall 13. The only purpose of this wall was to prove that we were going to get the same relative forces as we were with the hold downs that we were using on some of the other wall systems. The strapping we used in the lab were 2 traditional hold downs mounted seat to seat on the other walls. So here we did that for the strapping and flat straps all the way across the wall system. On the left-hand side, you can see one of the hysteric plots that was produced from applying that lateral load to the system and regulating that through the computer-generated graphics. So our conclusions, looking at these 12 wall configurations and the different level of detailing we used, we did find that the walls were detailed with full force transfer around opening resulted in a better global response. The stiffness of the wall increased, as well as the strength of the walls on all of the force transfer around opening configurations in comparison to all of the other approaches. So that's why we want to focus around force transfer around openings. When looking at your rational analysis methods, however, we also recognize that the drag strut technique was consistently unconservative. The cantilever beam was typically ultra conservative, which left us to decide whether to use the SEOC or the Dieckmann method as part of our design focus. And these two were the most economical design choices. So getting through that, that leads us to our 6th audience poll.
And much just like the other one, it's the same answers, a little different question. Which force transfer around openings method tested was found to be consistently unconservative? Is that the drag strut analogy, cantilever beam analogy, Dieckmann-Thompson, or the unicorn method? All right. And I think people were probably listening. So we've got 78%, 79, 80, and I'm going to close. So we've got 87% say the drag strut analogy, 6% cantilever, 5% Diekman Thompson, and 2% unicorn. And
It's always good to have fun.
Okay, Jared, there we go.
All right, yeah, so correct in A, the drag strut analogy. Hopefully this is a bit of a softball. That was the consistently unconservative version. So what's next? What else can we do to move forward with FTAO? Most of our feedback from engineers time and time again was on something similar to the wall 12 configuration. Multiple openings and asymmetrical piers. Now, before I move to our advancements, a note, if you're wanting to get more information on any of the research report is available on our website at apawood.org under the resource library. You can simply search for force transfer or the form number M410, and you can download our research and this documentation for free. This also brings me to the CEOC paper shown here. In 2015, Tom Skaggs, one of our research engineers in Tacoma, Washington, and Karen Beebe, another field service representative similar to myself, wrote a paper for the Structural Engineers Association of California convention titled Advancements in Force Transfer Around Openings for Wood Frame Shear Walls. This really focuses on the configuration of wall 12 that I just showed you all. Multiple openings and asymmetric piers. It is also the basis of our upcoming document that we're trying to put out. It's currently in development today along with a spreadsheet, and the report is on schedule to be released hopefully by the end of this year. And like I said, will be accompanied by that Excel spreadsheet that hopefully will help to make this an easier transition in using force transfer around openings. And both of these were developed along with our testing that was done in the laboratory. So here are a couple snapshots from the Wood Design Focus articles that I mentioned before with Zeno Martin. This really shed the light on the different analysis techniques, giving you very different answers. Also, as mentioned, Ed Diekman wrote back to Zeno in his original article and his own rational analysis approach. Mr. Diekman was also very kind when we did our first phase of testing, as shown in the laboratory. He provided us with design results for this same wall number 12 so that we were able to use his actual calculations in our comparisons. So now that we're at wall 12, looking closer at this wall system, this is the full force transfer around openings detailing. We have sheathing above and below all of the openings. You only have a hold down at the beginning and at the end of the wall, and strapping is provided above and below the openings. Again, you cannot see it, but blocking is provided on the interior side of the wall. We have multiple openings, 2 windows here, asymmetric piers, different pier widths for the entire wall line. So how do we provide an accurate analysis for this? That's what we wanted to set out to prove. So comparing the Diekman technique to the CEOC technique, there's some different basic assumptions. We're focusing on the Diekman technique for this presentation. Also, that's what we focused on for our conceptual keys and what came up out of the testing for FTAO. Not to say you can't use another technique, but using this method matched the testing most accurately in all of the forces. So the first assumption that we have in our conceptual keys is that you assume that the unit shear above and below the opening is equivalent. The second is that the corner forces are based on the shear above and below the openings and only the piers adjacent to that unique opening. So in the previous slide, we had 2 openings, and when you're looking at this distribution of forces, you're going to kind of break it down into each opening one at a time before you put it all back together. The tributary length of the opening needs to be calculated to define how much shear goes into each pier. So in the Diekman technique, you're not going to have the same shear horizontally for your full height segments. That's going to vary. It's going to be the same top and bottom, but not the same horizontally. So you need to identify the tributary length that applies over that opening to each of your full height pier segments, and that's based on the geometry of the panel lengths next to each unique opening. So the next conceptual key is to realize that we're going to take the tributary length, add it to the pier that you're looking at, and multiply that times your shear divided by the length of that specific pier. And this calculates the individual pier length horizontally, right? So we're looking for that first shear value on each wall segment. So the next step is that you have to be able to calculate the shear in all segments of the wall. We have those corner zones that have to be calculated. So that's based on the resistance minus the strap forces, and then we divide that again by the length of the pier. So we'll go through a design example so we can see this in a little bit more detail here in a bit. So as I mentioned earlier, the best part is the final conceptual key. So the final key is that when you're done summing all of the shears for the segments, you can check your work. The first vertical line and the last vertical line, shown here as lines 1 and line 6, should sum to equal the hold down forces. All of the vertical lines in between should sum to 0. This lets you know if you've done your math correctly. So you can check all of this at the end of the calculation. This is a lot of keys, and I know I've gone through them a little quickly, so we'll go through an example here in a bit to reinforce it and kind of show you what I'm discussing. So this brings us actually to our next audience poll before we get into our design example.
Okay, so which lateral design method do you believe is the most economical? Segmented, perforated, FTA, or force transfer around opening, or duct tape? I'm pretty sure it's duct tape.
Yep.
All right, we've almost got 80%. And here we go. All right, so we've got 71% say force transfer around openings, 18% say perforated, 8% segmented, and 3% are with me around duct tape.
Nice.
So, and
all right.
What do you say, Jared? What is it?
That one, there's no right, no wrong answer, right? So it's what you perceive and how you feel in your design. So what we're looking to prove, obviously, with our presentation and our testing is that force transfer is hopefully going to be the most economical choice. So as we get into this, we can look at that in a little bit more detail. And as most of us are engineers, building officials, and so on, some of this is going to be a review. But as I stated in the testing, we wanted to make sure that we looked at identical wall patterns and all of the methods that are currently available to us to see which one was the most economical, which one was the most accurate, and which one helped with our designs. So as we go through this shear wall design example, we're going to look at a segmented shear wall approach, the perforated shear wall approach, and the force transfer around opening approach, utilizing the new updated methodology that we came up with testing the Dieckmann design philosophies. So if we put this all into action, let's go ahead and look at this design example. So here's our wall. We will use this same wall for all three methods for an apples to apples comparison. Our wall is going to be 26 feet long, 8 feet tall. We have 3 openings in the wall, a standard 6'8" by 3.0 door, a 6 foot wide by 2'8" window, and a 2 foot wide by 2'8" window. It is important to note that we used asymmetric wall piers for this example, because that was the main portion of why we wanted to set up some of this testing, so that we could use the actual geometry of wall systems that we see in the field. So we have 2 4-foot piers at the interior walls and 2 3'6" piers, one at each end of the wall. We're going to be applying a 3,750 pound seismic shear load to this wall system. So beginning with the segmented approach, we ignore the contribution of the sheathing above and below the windows, correct? First, we'll look at the height to width ratios of the segments. We recognize that we have the 4-foot wall segments that meet our 2-to-1 aspect ratio, and the 3 foot 6 inch ones do not. They have to take that adjustment factor. So what we're showing here is the historic adjustment factor, 2 times the width of the pier divided by the height. For our 3 foot 6 inch segments, we would have to adjust only these segments by that 0.875 shown at the bottom right-hand corner. So this is an option. You could use the new adjustment factor that we spoke about previously, but then you would also have to perform that additional step of calculating the deflections of each pier to verify that it is the same for all piers. So for simplicity, for this example and for our presentation, we're only going to show the historic adjustment factor. So first, we start by calculating our unit shear. This is the 3,750 pound shear load divided by the sum of the length of the full height pier segments. So we add 15 feet total, which gives us 250 pounds per linear foot along the wall. Now we look at the allowable shear for our segments based on the sheathing values. If we look at the first, at the narrower 3 foot 6 inch shear walls, we're using 15 30-seconds rated sheathing, 8 penny common nails, 4 inches on center, and we have to apply that 0.875 adjustment factor to the 380 PLF, which brings us to 332 PLF. And of course, these values, for some of you are asking, are out of the SPIDWIZ table 4.3a, nominal unit shear capacities for wood frame shear walls. And as I spoke about earlier, we're using a seismic load, so that if you want to double check some of these numbers, you can feel free to do so. So this will yield that 332 PLF, which exceeds our 250 PLF design value, so we're good there. So now we're looking at the 4 foot wide walls. We're using the same thickness of sheathing, the same nail size, but the nailing can be reduced to 6 inches on center instead of 4 inches on center. Getting the shear value from our table, we show that our allowable shear exceeds the design shear, so we're good. Now we're going to calculate the hold down forces, which is our unit shear times the wall height. So 250 times 8, we need 2,000 pound hold downs, or hold downs capable of resisting 2,000 pounds of uplift. We'll need 8 of these hold downs, since we need 1 at each side of each pier we used. So again, for simplicity, I know a lot of you are thinking, well, we could use the dead load of the building. We're going to remove that just as a footnote, and the footnote adjustments, just so we can do this for the ease of calculation and our presentation. So quickly, we'll look at the summary for the segmented approach, and we'll review this again in a bit when we compare all 3. We're going to have 15 30-seconds rated sheathing with 18 nails at 4 inches on center. At the outside 3 foot 6 inch walls, 15 30-seconds rated sheathing with 18 nails at 6 inches on center at the interior walls, and we're showing 8 hold downs with a 2,000 pound plus capacity. And then our attachment at the base of the wall has to also equal the 250 pounds per foot, right? So now let's look at that same exact wall using the perforated shear wall method. So looking at our aspect ratios, we have the exact same values as we did with our segmented approach. The 4 foot walls meet our 2-to-1 ratio, but our 3 foot 6 inch walls must still be adjusted, right? So we have that same factor at that wall. We'll start out again by calculating our unit shear. This is the 3,750 pound shear load divided by the sum of the length of the full height pier segments. Again, same wall, so 15 feet total, which gives us that 250 pounds per linear foot. Now we need to take a look at the percentage of the length of the full height sheathing versus the entire length of the wall. Taking our 15 feet, dividing that by the 26 feet, we come up with a value of around 57%. Now we get our maximum opening height, which no brainer is our door, correct? So 6 foot 8 inches tall. And this is where we go in and we find our shear capacity adjustment factor, or that CO factor, that we need to use to adjust the value of the shear. So taking into account a percent of the full wall height and maximum opening height, we take that 57% that we just calculated, find our 6 foot 8 on the top, and interpolating between the values we end up getting that 0.61. So also, if you're still not completely sure about your opening height, if you want some flexibility, you can look at the top of the chart here and you can see that the opening heights are also given in a ratio, so you can find out what your wall is capable of and design your opening heights based on that as well, without having to know your design heights going into the chart. So we come up with this capacity factor of the 0.61. So now that we have our CO factor from the table, we use that to adjust the allowable shear value of our sheathing. Going back to the SPIDWIZ table 4.3a and looking at the 15-30 second sheathing with 8D penny nails, we have to go to a 3-inch on center nail spacing in order to achieve our design value. So we took the 490 PLF allowable shear, multiply that by the shear resistance adjustment for the 4-foot walls, and by both the aspect ratio adjustment factor and the shear resistance adjustment factor for the 3-foot 6-inch walls. So you see for the 4-foot walls, we end up with 299 pounds per foot, which is greater than 250. And then for the 3-foot 6-inch walls, we actually have to go down to 262, which is still greater than 250. So we're good at 15-30 seconds rated sheathing with 8D nails, 3 inches on center. So stay with me, we're almost there. This perforator approach does take a little while. So now that we have our sheathing determined, we can move on to calculating the uplift at the ends of the perforated shear wall, which is equal to our hold down force of R, right? So this is defined as the unit shear multiplied by the wall height, so 250 times 8 divided by the shear resistance adjustment factor of 0.61. This gives us roughly 3,280 pounds. Next, we calculate the in-plane shear anchorage, or the Vmax, which needs our unit shear of 250 PLF, divided by the shear resistance adjustment factor. And this gives us roughly 410 pounds per linear foot, which is the value used to design our collectors, or the drag struts, between full height wall segments at the top of the wall system. Next, we have to take into account the uniform uplift anchorage value that will be used to design the minimum wall base plate attachment to the foundation. This is only used at full height wall segments and is equal to the in-plane shear force at the top of the wall, so that 410 PLF. Finally, in looking at the deflection, we input our calculated Vmax and sum of length values into the equation 23-2 of the 2015 IBC. Again, for simplicity, I'm not going to go through the full deflection equations here, but we can definitely get that to you if you want it for the example after the presentation. So looking at a quick summary, our aspect ratios, we have the exact same values as we did for the segmented. The 4-foot wall met the 2-to-1, so it did not have to be adjusted. The 3-foot 6 walls did have to be adjusted, but either way, we came up with the same nailing throughout of 15-30 seconds rated sheathing with 18 nails at 3 inches on center. We only have 2 hold downs instead of the 8 on this one, so we have 3,280 pound hold downs. And our attachment at the base of the wall also has to be done for the 410 pounds per linear foot. So that's higher than that 250 pounds per foot that we had earlier. Okay, we're there, we made it. Let's finally look at force transfer around openings. So if we take the same wall in geometry and we apply the force transfer approach, we're going to begin our wall beyond the doorway. So the reason why this is because of that first conceptual key, right? We're assuming that we have an equal distribution of shear above and below our openings. So with the doorway, we cannot include it because we don't have any sheathing below the opening. So in this case, we're just going to start it at the location shown here. We check the height to width ratios using the height of our windows instead of the height of our walls, which is only 2 foot 8 inches. So we don't have to worry about taking any adjustments. We easily meet our 2-to-1 aspect ratios, and all of our walls are greater than 2 feet in width. So we're greater than the minimums required by code. We still have the same shear applied to the wall. So our next step is going to be to calculate the hold down force, and the hold down force is the 3,750 pound shear force at the top of the wall, multiplied by the wall height, and then divided that by the length of the shear wall that we are incorporating, so the 19.5 feet. So in this case, our overall length is the full length of the shear wall, since we are counting on the sheathing below the openings to help us resist our shear load. It also aids in the rigidity of the wall system. So this is another advantage to using force transfer around openings. When you calculate your hold down forces, in the other two methods, we were only able to use the sum of the lengths of the full height segments, but not in this case. We can use the entire length of the shear wall that we're initiating. So the second step is to then sum the unit shear above and below the opening, essentially taking the hold down force of 1,538 pounds that we just calculated and dividing that by the sum of the heights above and below the opening. So HA and HB shown here, which gives us our 289 pounds per linear foot above and below our openings, where those VA and BBs are shown on the diagram. Step number 3 is to find the total boundary force above and below the openings. To do this, we look at the openings individually. So for our first opening, we take our unit shear that we just calculated, and we multiply that by the length of our first opening. So 288 pounds per linear foot multiplied by 6 feet, you get roughly 1,734 pounds. Our second opening is narrower, so we only have the 578 pounds. So step 4, we're going to calculate the corner forces. We have 2 corner forces for each window, top and bottom as shown here. So on the wall system as a whole, we're going to have 4 corner forces for these openings. So if we look at F1 and F2, you'll notice that these are the same force because we have the same geometry for both of the adjacent wall piers. Both piers adjacent to this opening are 4 feet in length, whereas our calculated force is going to be 866 pounds for both of these forces, since they have the same tributary widths. So if we look at F3 and F4, we're going to get different forces due to the fact that we have asymmetric piers on each side of this opening. So the forces we calculate for F3 and F4 are as shown: 308 pounds for F3, 269 pounds for F4. So these are where we're going to get the forces that are required for our straps. So we're looking at an 866 pound strap force. The next step is to calculate the tributary length of each opening. We'll calculate the tributary length of the first opening, T1, based on the geometry of L1 and L2. This is pretty straightforward for most of us. In this case, T1 and T2 again are going to be equivalent because we have the same length for the walls, L1 and L2. So our tributary widths for the first are going to be 3 feet each. T3 and T4 shown at our second opening are going to have different values based on the adjacent pier lengths. So T3 is equal to 1.1 foot and T4 is equal to 0.9 feet. Step 6, so these are all those conceptual keys and steps that I talked about earlier. Getting through this, we're almost there. Finally, calculate the unit shear beside the openings. Here we'll use the shear to the middle pier for an example. We need to take the sum of the tributary length T2 plus the length of pier 2 plus the tributary length T3 and divide that by our length L2, okay? By the overall length of the wall. So looking at V2, we take 3,750 pounds divided by our 19'6", which is the length of this wall system that we are utilizing. Multiply that by the 3 plus 4 plus 1.1 that we just calculated, or the 8.1 feet, and divide that by 4 feet. So this gives us our 308 pounds per linear foot. And again, I can get you guys extended calculations on all of these if you want that at the end. So just as a check, we can take the sum of our calculated shears multiplied by our opening lengths. V1 is 337 pounds times 4. V2, 338 times 4. V3, 244 times a 3'6". And this should all equal to the total shear at the top of the wall. So if we multiply all these out, we should get that maximum shear applied to the wall of 3,750 pounds. It does check out, so we're good to go. So to finish the design, we have to calculate the corner forces in each of our segments. The first step is to calculate the resistance to the corner force, which is simply the horizontal shears that we calculated times the length of the pier. So we get the value shown on the left, 1,346 for the first wall, 1,551 for the second, and 853 pounds for the third. And then use that resistance and subtract out our corner force, and we get our resistance shown in step 8 on the lower right-hand corner. Take that difference of each of those resistances from the strap force that we calculated earlier, and then take that difference divided by the length, and it gives us our corner forces. So we're looking for these corner forces. VA1, VA2, and VA3 are our forces above the opening, and then we have forces below the opening. Assuming that they are equal, our unit shears are going to equal the 120 PLF for VA1, 194 PLF for VA2, and 160 PLF, 67 PLF for VA3. My apologies. So what that gets us is to allow us to get to that final step, that final design conclusion, to make sure that we can calculate and sum all of the internal forces of the wall to 0 and all of the external forces on lines 1 and line 6 should equal our hold down forces. So not going through that here, we look at this last step, and being able to check all that work lets you know if you did your calculations correctly. And again, as I stated before, we are developing a spreadsheet to help with all of this, to help automate it, and I have design examples as well as documentation that can help you with the design steps if you want further instruction on these as well. So if we get to our FTAO summary, after all those 10 steps, it breaks down to the same thing that we had on the others, right? Our resulting design shown here, we have the same sheathing that was used for the segmented wall, 15/32 rated sheathing, 8D penny nails, 4 inches on center. And I know we're roughly 800 or 8 PLF above the OSB allowable. We're considering this to be within our engineering judgment to allow for this wall system to work. We also only need 2 hold downs, similar to the perforated shear wall, the outside. These are going to be equal to that 1,538 pound capacity or greater, okay? Our shear connection at the base of the wall is at 388. So let's put this all together. Let's look at all 3 of our design assumptions side by side. So if we compare all 3 of the methods we just went through, we can see some similarities, but FTO appears to have the greatest benefits, in my opinion. All 3 used 8D nails and 15/32 sheathing with force transfer round openings and segmented using the least amount of nails. So I know some of you are thinking that this is a wash, right? And I agree, because I mean, let's face it, if we specify 4 inches on center and 6 inches on center on the same wall, typically when we go to inspect the wall, our framer is going to have this nailed around 3 inches on center for the entire wall anyway, right? So we can say this is a wash and all 3 walls are identical. If we look at just the hold downs, the force transfer round opening method has 6 fewer hold downs than the segmented, and although similar to the perforated method only having 2, the hold down capacity is approximately half of that required for the perforated method. We're looking at roughly 1,538 pounds for the force transfer method at each hold down capacity, and 3,280 pounds at the capacity for each hold down for the perforated method. So we're about half the capacity, which could help reduce the cost of the hold downs. And in the argument before, if we look at some of the dead load or any that we put on the structure to help resist these forces, we may be able to reduce the force transfer hold downs down to 0 a lot easier than we could with the perforated forces. So one other question you might have is, why would I use force transfer around openings if I can do the segmented approach? Well, we use this design example where you could use any of these methods just to show the flexibility in the design, right? We also moved to the opposite side of the door for the FTAO. So you may be thinking this isn't really apples to apples, but I just wanted to show you that we're getting better values and utilizing less wall. So for this design example, we're utilizing less of the full wall system, and we're still getting better design values for what we came up with force transfer around openings. If we did the same thing with the perforated wall, we could probably reduce some of the nailing down to that 4 inches on center, but we still end up having higher hold down forces no matter what we do. So again, I know you're all thinking the APA is crazy at this point, right? Because we're being very generous and we're giving you guys 4 foot or 3'6" or 8 foot tall walls. Everything's pretty ideal. When typically what we see are these 2 foot or 18 inch different size walls. Well, let's look at this just for a quick example and just for argument's sake. If we look at 4 different wall piers, P1, P2, P3, and P4 on this example, we have 2 3-foot piers at the interior and 2 2-foot piers at the exterior, okay? We have a 10-foot high wall system. Again, our overall wall system is 26 feet long. And just for the segmented and perforated, they may not work. If we look just at aspect ratios, the maximum aspect ratio of 3.5 to 1 on a 10-foot wall is around 34 inches. So to use either segmented or perforated, we would only be able to use the walls shown as P2 and P3 here, right? Those are the only ones greater. So that's all that would be resisting our load. P1 and P4 are too narrow. The nailing, hold down, and shear forces may instigate way higher forces to where these piers wouldn't be able to handle that loading. But if we look at this thinking about force transfer around openings, we only have to take into account the height of the panel adjacent to the largest opening or adjacent to the openings. So ignoring P1, as we did in our previous example, to get around that door opening, if we look at the opening height of 7 feet for this large window, that gives us a 24-inch minimum at 3.5 to 1. So we can utilize P2 and P3 and P with the adjustments, right? And P4, being adjacent to a 4-foot opening, can be used at a 2 to 1 aspect ratio with no penalty, because our 2 to 1 is 24 inches for a 4-foot opening, so we're good to go. So this is another instance of some of the things that we saw in the field with larger openings and still being able to utilize the actual geometry of the wall system. So another question that came up many times following our first phase of testing was, well, what about deflection of these walls and the drift on a perforated wall? How can I accurately design for this? And so we looked at the data and applied the historical 4-term deflection equation for our wind designers. You know that there is this historical 4-term as well as a new 3-term equation. We're using the 4-term equation, again, just like our previous philosophy, to get the most accurate out of each term. So we wanted to make sure that we had the most accurate nail slip, most accurate hold down slip, everything for our laboratory testing. So we're only looking at the full height piers, and those heights are going to be limited if there is sheathing resisting the deflection. So if we look at here on the top left, we have height 1, height 2, and height 3. Our design assumption is that if we have the shear force V forcing this wall to the right, the sheathing below the openings is going to be resisting the panel deflection for the panel 1 and panel 2, so that you're only going to see that deflection from the bottom of the opening to the top of the wall. Then the wall panel H3 is showing at the end of the wall system is going to have full deflection for the full height, because there's nothing resisting deflection outside of that wall line. And vice versa, in the bottom right-hand corner, you get the negative deflection. So we have the opposing deflection shown for that wall system. So the theory is that the overall deflection of this wall system is going to be the average of all 6 of these deflections. All 3 of the deflections in the positive direction and all 3 in the negative direction. So again, many of you likely have a deflection spreadsheet set up in your office, and this is easily automated in a spreadsheet, but it will also be a part of the accompaniment of the spreadsheet that we are developing. So in this case, we have a lot of data points to compare to our testing. But what's important to note is that the results based on using that analysis technique did match the backbone curve that was for wall 4 as well as wall 12, where we had multiple openings and asymmetric piers, if you remember the walls that I showed you earlier. And most of our analysis was done for that wall buildup 12. So our calculations and the laboratory testing matched up closely for what we determined as our deflection method. So this will bring us to our audience poll number 8.
Okay, and this last one is a true or false. So let's see here. Wall sheathing can aid in force transfer around openings, tension, force, resistance. Is that true or false? And this is our last poll question, so go ahead and vote. Got about 70% of you. All right, I'm going to go ahead and close it. All right, so 70% say true and 30% say false. And Jared, I'm going to let you discuss that answer.
All right, so the answer is true. Wall sheathing can aid in the force transfer around opening, tension, force resistance, and that was proven in our laboratory testing on wall 6 that I showed you before. And in reviewing the table that I showed you before, especially for the drag strut analogy technique, it did help specifically for that technique in the design examples and laboratory testing. So getting to that, the she-shaped panel, as noted in our testing, did reduce the amount of strap force required if your contractor, your client is focused on eliminating as much hardware as possible. This is something potentially to consider. You might be able to look at what you're doing at your strap forces, and if you're calculating that and simply take a C-shaped panel perhaps, you can eliminate some of those strap forces, which might help to eliminate the strap altogether. So at this time, like I mentioned before, we do not have anything additional engineering analysis that stands behind this on a calculation basis, but it is something that you can do into a rational analysis for something that could be developed in the future. So in this picture, note you see that the force transfer around openings of the panel was cut, or the opening was actually cut into the full length of the panel. The other thing you may notice is that although they only needed hold downs at either end, they provided hold downs on the interior as well. And the question is, well, is that a problem? I certainly don't think it's a problem. It'll make the walls stronger in rigidity, but as we've shown in our testing, and as is stated, the minimum is only the hold down at each end of the wall system. So that's all you really need for force transfer around openings. Making sure that this is all detailed correctly and designed correctly can help to recover the most economical design and what's going to be the best design for safe construction. So as stated, benefits for force transfer around openings with the continuous wood structural panels. For the structural engineer, the straightforward rational analysis. I went through a lot of conceptual keys earlier and a lot of steps, and especially in the design example, but it's very straightforward, basic math that can be automated in a spreadsheet. And if you use Excel or even another web-based application, it's easy to accommodate. So my favorite part of all of it, of course, is that you can check your work at the end of all your calculations. And here, what you're seeing on the screen is the short summary table, the basic calculations that gets us to the sum of 0 for our internal wall forces and the hold down force check at wall lines 1 and wall 6 to make sure that we're verifying our calculations. And this was done in the Excel spreadsheet that we are helping produce and verifies the design example that I took you through a little earlier. So we wanted to make sure that all those forces were coming to zero at the interior. Also, as noted, the value proposition of being able to minimize the number of hold downs and hardware on the project as a whole. Looking at these walls as a larger perforated wall, you can have a single hold down at each end of the wall instead of having to place multiple hold downs at each opening or each wall line. And also, obviously, depends on the overturning loads. Might be able to reduce these all together with the dead load addition from your structure, and hopefully that will help you reduce the overall hold down and hardware on the project as a whole, which also would mean fewer callbacks, less inspection time, less everything for the project, correct? So as we started, hopefully as we went through this demonstration, you were able to get through the learning objectives. We began by investigating what was going on with APA and our laboratory research. We looked at all the different ways that we could use FTAO and for multiple openings and asymmetric wall piers. And we looked at some of the studies in correspondence with FTAO and in comparison to the other design methodologies that are out there currently being done. So thank you all again for joining us here in our webinar. This concludes the American Institute of Architects Continuing Education Systems course. We will be open for questions and concerns here shortly, but Marcy first has a couple of things for you.
Right, and please stay on. If you want your credits, make sure that you stay on so that you're on for an hour and 21 minutes at least in order to get your CEUs. I'm going to take the screen back so that I can go through my slides real quick. Thank you, Jared, and thanks to all of you for being a part of one of our highest attended webinars. I'm going to go through some quick information. Our partner organization, WoodWorks, provides wood project assistance and other resources. If you want to reach out to them, just email help@woodworks.org or visit their website at woodworks.org /project assistance. You can also request assistance from them on our survey. I just want to make sure you're hearing me. And then design professional membership. In order to help design professionals stay informed about technical issues affecting the wood industry, we offer a design professional membership. There are lots of benefits, including discounts on our publications. Just check out our website if you're interested. We also have a Code Official Connections benefits program. There's no cost to qualifying participants who are code officials or inspectors, plan examiners. Again, check out our website for information on that. And then follow up, again, remember there's a follow-up email today. I know the slide says 30 to 40 minutes after the webinar, but given summer schedule and the large number of you today, please give at least an hour or so for processing before you get that email. In that email, there's going to be a survey. Complete that survey for a chance to win a free publication. Check out the information about your certificate of completion and CEUs. Note that the actual certificates will be available within 2 weeks of today. And remember again that in order to receive credit, you must have been present for 90% of the 90-minute webinar. That's 1 hour and 21 minutes. And then join us again on September 21st for a webinar on fire resistance in tall wood structures. If you have any other questions or want more information, just email us at education@awc.org or visit us at www.awc.org. All right, thank you once again for your attention. And now back to Jared and Michelle for some question and answer time.
Great. So we'll go ahead and answer some of the questions that were written in throughout the webinar. Thanks, Jared. That was a great webinar, and there was a lot of interaction between the audience asking questions. And are you ready?
Yeah, course.
All right, awesome. So one thing is, could the report, the testing report is M410, is that correct?
Correct.
And in that report, are there actual example calculations that have step-by-step examples on doing the whole methodology for force transfer round openings?
I believe so. Pretty much the exact same design example that we went through for force transfer round openings today is included in the M410, and it should lay out the steps as we did today, as well as that CEOC paper that was written by, I don't know if you can see my screen again, but this paper written by Tom Skaggs and Karen Beebe also contains our methodologies based on the testing.
Great. And then it was, are there other, there's a lot of questions about other examples, and I know you mentioned spreadsheet. They're wondering when that will be available and what other calculation examples are going to be available.
Great. Yeah, so currently we have slated for publication in the January 2008 issue of Structure Magazine. So I know most of you that are registered professional engineers received that document. We are going to have a technical topic design article that is going to potentially be published in January. It is going to be on the same topic with a different design example. Again, it's going to be the asymmetric piers and multiple openings. And we are currently in development on the publication and spreadsheet, and are hoping to have that completed and on the APA website before the end of the year, and it's all going to be free download. So.
Oh, that's awesome. Okay, some other questions that came in, and one has to do with the reduction factor, the aspect ratio, if it applies to both, if it's just seismic, or if it applies to both wind and seismic.
Historically, it was only seismic. In the 2015 SPID-WIS, it actually was updated to accompany both wind and seismic loading. So no matter what you're doing, design-wise, your building has to resist lateral loads, and the walls that you use need to have one of the two adjustment factors applied to the wall system.
Yep. And then there was questions related to measuring the aspect ratio given the three different methods of shear wall analysis. So maybe maybe on slide 10, you could show that. Is that shown on slide 10? Right, starting there, between, okay. You know, just go briefly where you measure the height and width.
Yeah, so typically for a segmented wall, we're looking at this, the wall segments, the aspect ratio for the height is measured from the bottom of the sill plate to the top of the double top plate, so the full height of that wall. And the width, the BS value, is going to be from the edge of that to the adjacent opening. If we have multiple openings, it's whatever the width of that wall pier is between those openings. We're going to have the same value for perforated, the exact same. We're going to be measuring height from the base of the sill plate to the top of the double top plate. Width is going to be the exact same as well. And then looking at force transfer, this is in my eyes the biggest benefit, because our height is only the height, the rough opening height. So we're looking at the bottom of the top plate of the opening and the top of the sill of the opening, and that rough opening height. And then our width is going to be whatever the wall pier width is between the end of the wall and the opening, or between openings.
Great. And then for a segmented approach, if you have platform construction, and say you have a 2-story shear wall, but platform framed, what is the overall, do you measure the overall height from roof to foundation as your height aspect ratio, or is it from, you know, where do you measure it for that 2-story shear wall that has platform framing? Right,
so you would typically measure it from the top of the foundation or bottom of sill plate to the top of your double top plate. So if we have platform or balloon framing at a tall wall or great room area where you have a 16-foot tall wall, it would be essentially the height of your stud plus the double top plate and the sill plate.
Okay. And here's another tricky one. What if you had an opening, say, that's shown right there, and then one below it, 2 openings? What do you measure? Is that something that you can give guidance on? A stacked opening?
Yeah, typically if we do stacked openings, then you just consider it as one opening. So if we have 2 2-foot openings with 1 foot in the center, then you're going to end up with a 5-foot opening. We're still only accounting for the shear above and below the openings with that sheathing resistance. Technically, you could probably use the values, but it was not tested. So I would just accompany it with the full height and subtract out whatever sheathing is in between openings.
Okay. And then there's a lot of questions on the overall geometry, which these are really good questions. One is, are there minimum requirements for the height above the opening? And then also, what if you had a 2-foot opening, a 2-foot from the sill plate up only 2 feet? Is there any minimum dimensions for above and below?
No, there is not. So really the only minimum dimension that's called out for code-wise is your wall pier has to have a minimum width of 2 feet, right? 24 inches. Above and below the opening, the only thing that's going to cause you to have a limitation there is what the capacity of the structural system is going to be. So at the maximum capacity of 10 D nails, 2 inches on center, structural 1, 15, 30 seconds, that value of the PLF value of the sheathing is the only maximum that resists, because you're going to end up with larger strap forces, the least amount of sheathing you have. So, but that's the great part about force transfer around openings, is it can act with the actual geometry of the wall system.
Okay, good questions coming across. Here's one about the testing. Did you provide 2 2x or 3x framing members in your test panels at all panel edges due to the nailing?
It was double 2x.
Okay.
Double 2x4.
And then another one related to the blocking around the opening. Does it matter orientation of the blocking, and does it have to be tightly fit, and how does it accommodate the strapping? A lot of questions about that, about the blocking.
Yeah, it does not actually. With any sheathing, any wall sheathing for lateral shear design, the orientation of the blocking isn't as important as having the blocking in place. So we actually recommend having the blocking flat to the sheathing. That way you have a broader, if you're using a 2x4, then you have the actual full depth of 3.5 inches to be able to hit from the opposite side of the wall rather than 1.5 inches, right? So you have a wider area to hit. And as long as that blocking is on the backside and is between the studs and allows for the nailing to go through the sheathing into the blocking, you're going to get the full resistance down the shear wall path. So
there's a minimum depth penetration requirement.
Right.
Right. Okay.
Typically the 1.5 inches.
Yeah, as long as you meet whatever that requirement is. Okay, for the straps, do they need to be across the full length of the wall? And here's another one. Is there any issues with strapping across blocking on the unsheathed face of the wall? Must the strap be on the same side of the sheathing?
In testing, we tested it on the outside. I've seen it done both ways. In discussions with our technical services department, we didn't see an issue with having, the strapping on the interior side of the wall. But for the most part, we have the strapping for the tension forces at the exterior of the wall, and we're resisting that with the compression forces with blocking between studs at the interior. So we typically like to see the strapping on the outside of the wall. I know in some areas that does affect the veneer attachment, but and that's typically what they're looking at.
So that's under the sheathing. I think this question is on the other side, the unsheathed side is what.
The strapping at the interior of the wall.
Right. Like
Right.
the drywall side if it was only a one-sided shear wall.
Yeah, for our testing and for the documentation, we typically did the strapping at the outside. It wasn't tested at the inside, so I don't know.
Yeah.
Really, what the comment would be on that. So I don't think you wouldn't really have as much anything but the sheathing resisting the forces at the outside of the wall. So that's what it's in place for.
Mm-hmm. And what's transferring the load across that?
Right.
How can finite element analysis of force transfer around openings compare with the three methods? Was there any modeling of that?
Essentially, for what we did the three different methods, and we had the laboratory tests physically done. But that finite element analysis method is where the University of British Columbia came into play, and we had them do the finite analysis via the computer to make sure that we were getting identical or very similar values. And it turned out that we were getting very close values, and based on our testing and their computer analysis. So it's pretty much apples to apples on what we saw.
That's good.
And that's all included in the CEOC paper that I showed you earlier on how the testing was completed. And
then, so was that the only computer program analysis that was done through them? Someone was asking how were there any other methods that were used besides spreadsheet or the finite element analysis?
Yeah, that was it. They technically did the finite element analysis. The only thing we used the computers technically for was to apply the load and measure all of the reactions from the wall system and get our hysteric plots so that we knew what the forces coming back from the hold downs on the corners and everything on the wall was. And other than that, that was pretty much it.
Okay, so we'll have one last question. I know there are a lot more. Jared has agreed to go through some of these questions with us later, and we'll follow up. But here's one last one. In the design example of the three walls, I don't know what slide number that is. Let's see, slide 71. Oh, you went right to it. Okay, you're paying attention. Okay, yeah. This on the force transfer around the openings, the first pier actually, from going from left to right. What would happen if you use that as part of your lateral system? How would a comparison be? And I know this is like off the top of your head.
Well, no, I mean, technically, based on the methodology that we studied in the Dieckmann method, you technically cannot use the first pier because we are estimating the resistance above and below openings to use our strapping, correct? So you can't use that very first pier because there's no way to transfer load around the bottom of the door opening if we have no sheathing resisting. So that's why in the design example, we moved to the pier on the opposite side of the door because we have no way to utilize the first wall pier.